Well, here we are at the second talk. And you remember when we left, we had a couple of questions. We had a great tank of water, or bay of water, and there's all the water. And down underneath, we had a block of wood. And of course, there was a certain buoyant force pushing up on the block of wood. And then if we brought the block down deeper, suppose we brought it down to here. We drug it down here. When we got it down here, what would happen when we got it down to this new position? Pushed it down into this new position here. Would it be more buoyant or less buoyant? Or maybe it would have the same buoyancy. Of course, a lot of people will think that it will have more buoyancy down there because there's more pressure down there, and they just feel that the deeper you go, the more buoyant it is. Well, let's figure that out and see. Let's see how that works. Let's make some numbers. And I'm going to say 1, 2, 3, 4, 5, 6, 7. This represents the increasing pressure as you go down in the ocean. Now you'll ask, what? 7 what? 7 pounds per square inch, 7 newtons per square centimeter. I don't know what. I'm a simple-minded guy. It's just 7 is the pressure. 7 something. 7 something is the pressure. Because you don't have to worry about that to understand the principle of this. You don't have to go that deep into understanding exactly what the units of pressure are. Now, let's put the block right here where the 2 was. I erased the 2 and I put the block here. Well, how many pounds are pushing up on the bottom? 3 pounds pushing up on the bottom. How many pounds are pushing down on the top? 1 pound is pushing down on the top. Well, if you have 3 pounds pushing up and 1 pound pushing down, what's the net force? Well, the net force is 2 pounds pushing up. Now, let's take the block away from there, and the water will go back in here again, and the 2 is back here again. And let's insert the block deep down in the water down here. Okay, here's the same block. Now, what's the pressure pushing on the top, trying to push it down here? Well, here it's 4 is pushing it down. What's pushing it up? 6 is pushing it up. Well, if you have 4 pushing you down and 6 pushing you up, what's the balance? The balance is 4 minus 6 equals 2, with more force pushing you up. So still down here, the upward force is still 2 pounds. So you see, it doesn't matter. When we went down from here, it was up 2 pounds. When the block was here, the upward force was also 2 pounds. And no matter how far down we go, the buoyant force will stay the same. It will always be 2 pounds. Now, you have to be a little bit careful because here's where the theoretical mixes with the practical. And always there's a lot of wise guys that know about a practical thing, but they're so concerned with the practical thing they forget the principle. In this thing we emphasize the principle. But now, in practice, supposing this were not a block of wood. See, I was very careful at the beginning to say we're going to use a block of wood, and I said it's a solid block of wood. But suppose we had a little balloon here. This is a tiny little balloon. Okay, there'd be a certain force of buoyancy on that there too. And if I put the balloon down here, of course, the force of buoyancy on the balloon when I got it down here would be the same. Remember, in fact, you know the rule. The rule is in this case is, well, there's a pressure on the top, pressure on the bottom. It's equal to the water. The buoyancy is the water that would have filled the balloon minus the weight of what's ever in the balloon. Maybe nothing's in the balloon, so then the pushing up is just the weight of the water that would fill the balloon. But now comes the practical point. When you get a balloon down here, will the balloon be the same size that it was up here? No. You're down deeper in the drink, and a thing like a balloon will actually be smaller. And so there's less water that would go inside of it. It has less square inches on its top, less square inches on its bottom, so there's less force to work on it. And what actually happens is the thing, instead of becoming more buoyant, if it has less surface, it interacts less with the water, and it's less buoyant. And maybe the buoyancy down here would only be 1. It would be less than the buoyancy up there. So things that lose volume because they crush actually lose buoyancy as they go down deeper into the water. And that even works for submarines. As hard as they are, you know that submarines are slightly flexible. And indeed, if they do slightly reduce their volume, they become less buoyant as they go down deeper in the water. Of course, it works for all kinds of things. Okay, so much for that. Okay, now, in the battleship, I want to actually show you how the pressure gets down to the bottom of the battleship between the tub. And so I'm going to draw a blow up. I'm not going to draw the whole thing. I'm just going to draw a real big, here's the side of the bathtub coming down. It goes down underneath. And here's the side of the battleship. And it curves down here and curves down underneath. And of course the tub is filled with water. And here's all the water that's underneath it. And I want to show you how the pressure actually gets down under the battleship. Now I'm going to have to draw in this space that I shaded in to show it was water here. So I'm going to have to clean it out again so I can draw in it because the shading gets in my way. But here it is. Here we are, right back again. And you understand that all this region down here beneath this line is filled with water. Now, what happens? How does the pressure get underneath? Well, first of all, let's imagine just a little thin in our minds, a little thin tube of water. And this tube of water has weight, and it presses down. It presses down here to this place here, and there's some water there, a couple of water molecules. Now, if they keep pressing down, you'll run into the side of the bathtub. Remember, this is the side of the bathtub over here. You'll run into that. So we don't want to run into the side of the bathtub. Actually, we don't need the side there. So here, the pressure has to go sideways. But remember, I showed you very carefully that pressure pushes in all directions. So if I say the pressure is pushing down here and then it goes sideways here, there's no harm in that. I don't lose any pressure by making a sideways step. And now, here I run into the battleship. So I can't go any further. So there's a molecule right here near the surface. And here, I have to make the pressure press down again. But I don't lose anything by doing that because remember, pressure pushes in all directions and I can stagger around any direction I want. Now, when I come down here, I not only have all my pressure that I had up here, I not only have all the pressure, I even have more. Because as I come down, I get the pressure that's on top of me, plus I get the weight of this column of water. Remember we had a column of water here? I had a weight of column water here. Now on these sideways steps, do I increase my pressure? No, because the pressure pushes, the weight of the water, there's water here, but the weight of this water is pressing down here. So I just keep the pressure here over to here. I don't increase my pressure. When I get over to the left, I have everything I had on the right-hand side. I don't lose anything, but I don't gain anything. But on my downward steps, I do gain. I have everything I had on top, plus I gain the weight of that column. I have even more pressure. And little by little, I can work my way down. The pressure goes this way, and then the pressure goes this way. And finally, the pressure gets under the ship, comes over to here. Maybe it even goes over to here. And then when I'm under here, I have all my pressure, and I can use it to push up underneath the ship. And there it is. Of course, when it comes up, you lose a little bit by coming up, but not much. Okay, and that's how the pressure works its way down. Of course, who knows what path it takes? There's a million different paths stepping down that it could take, and they all amount to the same thing because all the downward trips add up to the same thing, regardless of which path you take downward. Now, I want to show you something else. And that is this. You might still say, well, this is some sort of a balance. Let me, again, clean this out and draw this. And here is this water here. And here's this big, heavy ship. I'm shading this time in the ship. And maybe it's more appropriate to shade in the ship because it's the heavy thing. And there's a problem here that's worth appreciating. I'm not going to give the answer to it now but you should appreciate that there's a sort of a mental problem still here. And it's the same problem in a way that we started with. What does this ship weigh? Well, I don't know what this ship weighs, but it's something with a lot of zeros, huh? What's that? That's a million. Should we make it a, well, we won't make it a billion. It's not the national debt. But this is a million something, real heavy. What does this water weigh? Well, we know the water doesn't weigh anywhere near as much as the battleship. How many zeros can we fit in here? Let's say 10. 10 something. 10 pounds, 10 ounces, 10 grams, kilograms, whatever unit they want to be in vogue. Now let's think, there's sort of a balance here. What do I mean by a balance? If the ship were to come down a little bit, then the water would go up. Isn't that right? The water would have to go up if the ship came down. And if the ship went up, then the water level would have to come down. So in a very real way, this water here, this tiny bit of water, this 10 pounds of water, is balancing 1,000,000 pounds of ship. And you can see it because when one goes up, the other goes down. And when the other ship goes down, the water goes up. And it just doesn't seem reasonable that 10 pounds of water should be able to balance 1,000,000 pounds of ship. Of course it does, but how is that? How can it do that? Well, first of all, I'd like to show you that it does, and you can see it in another way. I'll show it to you in another way. Here, imagine a tube like this. And let's pretend this is a pipe. This is a big fat tube or pipe or tank, and it comes down. Here's a skinny tube, tank, or pipe. They're connected at the bottom. They're freely connected at the bottom. And I'm going to put some water in them. In fact, if I fill this one up with water to here, some of the water will go around and it will come up to the same level over here. We all know that the levels will be the same on both sides. And we also know that these things balance each other because we know if this comes down a little bit, this is going to come up a little bit. And if this comes down a little bit, the level over here is going to come down a little bit. And of course, things will be hunky-dory when they're at the same level. When it just balances, everything will be fine. We know this is true. And yet, it's again a mystery in a way because over here, honestly, we have an enormous amount of water. Maybe here we have 1,000,000 gallons of water in this thing. And over here, maybe we only have 10 gallons of water. And somehow, this 10 gallons of water is balancing the 1,000,000 gallons of water. It's something to really think about. It's an amazing thing. As I say, I'm not going to answer it right now. I'll answer it a few lectures from now in a slightly different context. You'll see the answer. You'll understand why there's really no problem here. But well, I shouldn't say that there's really no problem here. There is a problem here. You'll appreciate the answer. But you cannot appreciate the answer until you first appreciate the problem. And right now, you're going to begin appreciating the problem, I hope. Okay. The topic for this talk is where physics came from, how physics got started. Why is there a subject, if you come to school or you go to the library, there's one section of the school building or there's one section of the library devoted to a subject called physics. How did physics come to be a subject by itself? If I ask an audience that, a common response would say, well, people wondered how the universe came to be, how the universe began, how it ended. That's how physics came to be. Well, it's true, people have always wondered, but that's not how physics came to be. Maybe in the olden days. Physics began a long time ago, you know, the Greeks. How long ago did the Greeks live? Well, 2,000 years ago to the time of the Romans, and maybe another 1,000 years ago to the beginning of the Greeks. Not quite, but almost. It's a long time ago. People began to think about those things. And if anybody in those days wondered about how the universe came to be or how it would end, they thought that the province of that answer was theology and certainly not physics. You say, well, maybe people wondered what matter was. And indeed, maybe some people wondered what matter was. But those were just a few people, probably thinking about things while they were taking a shower. That's an academic thing. That's maybe how a university works nowadays. But physics did not begin in universities. Physics began, all important things come from something practical. And what do I mean by something practical? It means people want something. What do they want? What is it that they want? Well, it turns out it's awful hard. It's awful hard to find out. So another way to find out about a thing, if you want to know about it, is if you go to the doctor and you go tell the doctor, oh, my arm hurts. My arm hurts here down to here. You know, what's wrong, doc? It hurts in the morning when I bend it. Instead of worrying about your arm, the doctor asks you, well, do you have any sisters and brothers? Are they still alive? If they died, what did they die of? What ailments do they have? What about your father and mother? Are they still alive? What ailments did they have? What did your father die of? You know, that's how the doctor's going to figure out what's wrong with your arm. So if we want to know where physics comes from, we should say, hey, physics, do you have any sisters or brothers? Oh, physics has a sisters and brothers. What are the sisters and brothers of physics? The sisters and brothers are chemistry and astronomy. And now we can say, well, where did they come from? It turns out, if you want to know where they come from, all of these things come because there is a problem. Each of these come because people want something. Now, what do they want? Let's take astronomy. What do people want from astronomy? To know the names of the stars? No, they don't want to know the names of the stars. Who cares what the names of the stars are? It's something you read in a dictionary if you look it up. To find out what they want, maybe it's best to go back and think about what is astronomy? What is the old name for astronomy? The old name for astronomy is astrology. What do astrologers want? Astrologers want to tell the future. That's a very wonderful thing to be able to tell the future. A very desirable thing. You know, years ago, I worked for NASA, and I traveled a great deal and it became a bore. I was on the airplane all the time. One time I was on the airplane with my friend Walter Wysochanski. And just to idle the time away, I said, Walter, if you had 3 wishes, Walter, what would you want? And Walter said, he would only have 1 wish. I said, gee, that's very modest of you, Walter. What would that 1 wish be? And Walter said, I wish I could have next Friday's Wall Street Journal today. Isn't that an amazing thing? If you could have next Friday's Wall Street Journal today, that would be Walter's great wish. On Friday, when he gets it, you can buy it for 75 cents. And then the day after Friday, you can buy the Wall Street Journal for 75 cents per ton. But today, to know the future, there is something of enormous value. And the astrologers thought that somehow, by knowing about the stars, they could tell the future. You see, the problem was the astrologers believed that we on Earth are somehow controlled by the stars and the planets and the sun and the moon as they move around in the sky. And they believed that if somehow you could figure out where Mars would be 3 months from today, maybe you could figure out where you would be 3 months from today if you were controlled by Mars. Or maybe you could understand where Mars candy bar stock would be, if it would go up or down in value, if you could figure out where Mars would be in the sky 3 months from today. So that was the practical problem behind astronomy, or behind astrology. Now, there's something about these problems. There's something about these problems. These problems, it turns out, that get a science started can't be easy problems. Why can't they be easy problems? Well, because if the problem is an easy problem, you solve it right away. And after it's solved, that's it, you go on to something else. and the subject is finished. You work on it, but nobody else works on it after you because the problem is solved. You can tell how to predict the motion of Mars. On the other hand, the problem cannot be impossibly difficult. Because if the problem is impossibly difficult and you work on it and you make absolutely no progress, and your friend comes after you or your son comes after you, and he works on the problem and he makes absolutely no progress, and maybe his son comes after him and he also devotes time to thinking about the problem and he makes absolutely no progress on the problem, then in that case, very soon, people will be frustrated and they will quit. And they won't go on. So these problems that start sciences have to be problems that are not impossibly hard to make progress on, but they also cannot be problems that can be solved very easily, because if they were solved, they would go away. It has to be just a certain kind of a problem. Let me explain in other walks of life, other situations that are like that. These problems that get science started are like falling in love a little bit. You fall in love. Who are you going to fall in love with in your class? Who are you going to fall in love with? Well, maybe you'll fall in love with there's some girl in the class that she just likes you and she jumps all over you. Every time you go out from school, every time you go out between classes in the hall, this girl is right behind you. She follows you home. Well, that problem is too easy. That's not going to be the supremely attractive problem. You might even solve that problem, but it's not the supremely attractive problem. What's a supremely attractive problem? Well, maybe there's another problem, like you're in love with a movie star in Hollywood. The only thing is that you live in Winnemucca, Nevada, and you write her a letter, and you write her a second letter, you write her a third letter, but you get no answer. You make no progress on this problem at all. So after a while, you're going to lose interest in it, and you're going to cease to work on it. But it turns out that the problem that interests you the most, the girl that is most attractive, is the girl that is within reach, but possibly most difficult to reach, like the cheerleader or the pom-pom girl, or the ice skating queen, or somebody like that. That's who's going to be attractive. See, there's a chance she's in the class, you talk to her, you see her, you make eye contact, she says something to you, you say something to her. So there's a chance, but of course it's not a particularly easy problem to solve. That's the kind of a problem that begins a science. Let me give you another example in a whole different whole different frame of thinking. What is music? Let's talk about music for a minute. Supposing you have a noise like this. Boom, 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 boom. Well, you can tell what's coming next. Boom. Is that music? Most people would not think that's music, though I hear some people in automobiles passing me on the street that seem to think that's music. But the majority opinion, I think, is that boom, boom, boom is not music. Why is it not music? There's a pattern there, yes, but the pattern is too obvious. It's too simple. You know what's coming next. Now let me give you something else where the pattern's not at all obvious. And you say, boom, boom, bang, ding, ding-a-ling-dong. Well, is that music? Well, again, there are a few people that would say that is modern academic music. But I think, again, the majority opinion is that that is not music. Why is that not music? It is because the pattern, if it is there, it is impossible to discern. What makes music attractive is that there is a pattern, but that the pattern is not obvious. You can get the pattern, but it's just on the limit of your ability to get. And that's what constitutes music. And so it is with these sciences. Well, we talked a little bit about astronomy, the problem that got astronomy started. What is the? Let's talk about some other things. What is the problem that got chemistry started? Well, again, we use the old formula. Let's use the formula. Instead of people wanted something, but we can't tell what they wanted. They wanted to make nylon. Of course not. They didn't have any idea what nylon was. But we can find out what the answer was. We simply ask, what is the old name for chemistry? You see, history is a magic key if you know how to use it. What's the old name for chemistry? The old name for chemistry is alchemy. What did alchemists want? Alchemists wanted gold. They had an idea that you could make things that weren't gold into gold. What a crazy idea. These people must have been very stupid in those days. How stupid they were to think that you could make gold out of things that weren't gold. Everybody knows that you can't do that. Why, if you could do it, everybody would be doing it. Well, you mustn't think that these people that lived a long time ago were stupid. They were, I think they're stupid. They couldn't even wear a pair of Levi's. They had to wrap themselves up in a sheet. But nonetheless, they weren't stupid, because now the people that can afford to Levi's pay even more to wear Levi's that have holes in them. The Levi's that have holes in them cost more than ordinary Levi's. So who's stupid? But anyway, these old people who thought about these things, the same people who thought about alchemy, also thought about all these theorems in geometry. There's a theorem in geometry called the theorem of Pythagoras, and it has to do with right triangles. Right triangle, that's a triangle with a square angle. And if you build a square here, and you build a square here, and you build a square here, then if you take this square, A, and this square, B, and you add them together, you'll get this square over here. They not only discovered that, these old people not only discovered that, but they proved it. Now, I bet if you go to your high school mathematics class, maybe your teacher could no doubt recite the theorem. I wonder if the teacher could actually give a proof, could actually repeat the old Greek proof of this. I know in some high schools if some teachers could, but I'll bet that in most high schools the mathematics teacher could not recite the old Greek proof of this. So these people were very clever people to figure out things like that, not only to discover them, but to prove them. You have to have the highest respect for these people who thought that you could make gold out of stuff that was not gold. Well, still, why did they think that? I mean, granted they weren't stupid people, but why did they think that you could do that? Don't you know you don't get something for nothing? That's a basic principle of the universe. Well, they noticed that you can make things out of other things, and you can change the nature of things entirely. Let me recall something. One of the things you learn in Boy Scouts, and I think also in Girl Scouts, is how to make soap. Now, maybe we're not supposed to talk about Boy Scouts anymore, but I was a Boy Scout once, a Cub Scout. You learn how to make soap, Boy Scout soap. And of course, this was known to these ancient people too. They learned how to do things like this. And at least the ancient Chinese people have had it figured out. Do you know how you make soap? What two things you mix together? First of all, you take lard, grease, the drippings from when you cook bacon, the greasy stuff that you pour into a can. That's half of the ingredients for making soap. And you know what the other half is? When you have a fire, what's left after the fire is soot and ashes. You take the ashes, the white ashes that are left after you burn wood. Those are the two most dirty things in the world. If you ask which would you rather have to get your face into, some dirty soot or some dirty lard, it'd be a toss-up. You take those two nasty things and you mix them together in the right way, and you know what you come up with? Soap. It's amazing. You come up with something entirely different than you go in with. You go in with these two nasty things that you would never think you'd use for cleaning, and you come out with something that is used for cleaning. So the ancient people knew stuff like that. And they said, damn it, if you can make clean stuff out of dirty stuff, then there should be nothing to making gold, because look, here's all you do to make gold. It's real simple. Now, what is gold? Gold is yellow and heavy. Isn't that right? I think gold is real heavy if you've ever handled a piece of gold, and it's real yellow. And if you've also handled it, it's very soft. You can bend gold in your hand. Some people advertise that their coins are pure gold, like I think the Canadian maple leaf is pure gold, but a real circulated coin, like the American Eagle or the Krugerrand, a real serious gold coin would never be made of pure gold because it's too soft. So you take something that's soft and yellow and you want it to be heavy, so what do you take? You take lead. That's spelled wrong. And you take sulfur. Why do you take sulfur? Because it's yellow, and this is heavy, and this is heavy and soft. Lead's soft too. That's why you use it on wine to make seals for wine bottles, and they should come together and make gold. It's easier than making soap. The only thing is it doesn't work so easy that way. But the point is that in their heart, people felt that it had to work, and they also discovered all kinds of strange things were discovered, like phosphorus and whatnot, by playing around with various things and trying to make, if not this combination, then some other combination, trying to make gold. And though they never found out how to make gold through the process of chemistry, nonetheless, all kinds of things were discovered. All the knowledge we have in chemistry was discovered as a result of starting to do this. Later on, they realized they could never do this, but it was worthwhile trying to do other things. There's a little more to this story too about what people want. There's another side of this story that I should tell you too, about why people wanted to learn how to make gold. You see, there was a feeling that the process of making gold, there was another way of looking at gold. Most metal on the earth was corruptible. What do I mean by corruptible? What I mean by corruptible is that if you have iron, it will rust. If you have silver, it will tarnish. Copper will tarnish. What other things did they have in those days? Lead reacts with various things. In fact, everything, not only metals, but wood, most everything that people have, water evaporates, human beings die and rot, everything becomes corruptible in the world, but the ancient people knew one thing that was incorruptible, that is, it would not tarnish, it would not rust, it would last forever, and that is gold. Gold is, the reason for that is chemically that gold doesn't react with other things very easily. Of course, that wasn't the way they put it. They felt that there was something heavenly about gold, that it stayed by itself. And so they had an idea that if they could take ordinary things and take the corruption out of them, like if you could take iron and take the corruption out of it, decorrupt it, what would be left would be the pure gold, the thing that God put in, the incorruptible thing, minus the corruptible stuff. Now, of course, that was an interesting idea. If it would have worked, it would have been a way to make gold, but it would have been useful for something else too, and it would have had an even greater use. Because the same process that could be used for decorrupting iron and turning iron into gold could also be used for medicine. After all, people get sick. And why do people get sick? Because various corruptions get inside of them, and it causes their arms to shrivel up and funny pimples to grow on their face and all the ailments that come to a person. But if you discovered a process for taking the corruption out of lead or iron, you could also conceivably use that same process for taking the corruption out of human beings. And that would be a way to have medicine. In other words, you discover how to cure people of their various diseases. And therefore, there's a practical side to making gold. It's interesting that two things are interesting about that. First of all, that idea of medicine is still around. in a lot of New Age science. That's an underlying theme in a lot of New Age medicine. But also, it's the same thing that scientists use. Whenever scientists are working on some big process like going into space or some nuclear experiment, they say, but because of this, some little spin-off from this will lead to a cure for cancer. It reminds me, it's not very distant from the ancient argument. To make gold, okay. So that's the problem that started chemistry. And of course, nobody ever did it, but nonetheless, you could make startling discoveries if you played around in a systematic way, boiled things, cooked things. You discovered all kinds of interesting processes. Well, now we've talked about astronomy, and we've talked about chemistry, and now it's time that I come back to talk about physics. What is the problem that got physics started? How did physics get started? What did people want? And I'll tell you what they wanted. The problem that got physics started. The ancient people wanted to find a perpetual mobium. What's a perpetual mobium? That's an old-fashioned, elegant way of saying they wanted to find a perpetual motion machine. Not as a toy, but as a working machine. You know, the problem that all of us have is to do work. Now, of course, you got to buy electricity, or you got to buy gasoline. But everybody always says, there's a battery that will run forever. It's just that the electric company or the gasoline company doesn't want you to know about it. But if you got this battery, it would run forever. And of course, the reason is that once you had this thing, you wouldn't have to keep paying for gasoline and electricity. In the olden days, people didn't pay for gasoline and electricity, but they had an ox or a mule or a water buffalo, and they had to feed it. Or if you had a slave, you had to take care of your slave. It's very expensive, an expensive person to maintain, certainly to feed. You have to feed it well because you can get no more work out of a person than you feed the person. Or you have to work yourself. And so if you could find a machine that would somehow keep on doing work without being fed, that would be a wonderful thing. Now, why in the heck did people ever believe? What made people believe that such a thing was possible? Again, it's getting something for nothing. It sounds, were these old people dumb? Well, I've told you these old Greeks were not dumb. So if they were not dumb, where did the idea for such a thing come from? Well, I'll show you how the idea began. The idea began with just technical inventions. You know, probably at the very beginning, when people were still not very civilized, if you wanted to get a drink of water, you had to go down to the creek and stick your mouth down in the water and suck up some water. Everybody who wanted to get a drink of water had to go down to the creek and take a drink. And everybody who wanted to go up in the tree and get some bananas, if you wanted bananas, you had to go up in the tree to do it. Everybody had to go, one by one. But at a certain phase in civilization, and this must have been a huge advancement if you think about it, that there must have been some organizer. One guy must have said, hey, Joe, you go down to the creek and you bring back water for yourself and for Billy. And Billy, you go up the ladder there, up into the tree, and you bring bananas back for yourself and for Joe, who's going to get you water. You see what a great thing? Then everybody doesn't have to do everything. Now, as soon as you begin to do work like that, you have to bring some water for somebody else. And the first invention was probably to bring the water in your hands. You had to carry back the water for Joe and for Billy and for Ray and Susan, all in your hands. It's a hell of a thing. It's not too good because you can't carry much water and it leaks. And then people made the first wonderful high technology invention. They made a basket, maybe a basket with mud on it so the water couldn't leak out. Or they made probably the first one was a coconut shell or something. And then they made clay pots. And the clay pots were really great because if you had a clay pot, you could bring water up from the creek and you didn't have to bring it up in your hands leaking. It was a fantastic technological advance, just like a 1,000 transistor chip. In fact, the people are so taken with it that there's some people in the university that are still studying clay pots. They have these museums with all these clay pots, and they look at them, and they have the artwork on the clay pots, and they study that for a whole lifetime. But that was a big technical thing in its day. But it didn't end there. After clay pot came along, then people discovered, well, look, you can, if you go way, way down, you can climb down yourself. Maybe you go down a ladder, down into a creek or a well, and then you have to climb out yourself. And then somebody said, look, I got this other idea. We'll make this thing called a rope. With a rope, that's a great invention, because if you have a rope, you can just send the bucket down by itself, and you don't have to go down. Then you can pull the rope up, and the bucket full of water will come up without you going down to get it. And then somebody else made an invention that instead of having the rope go through your hands, you can put the rope on a wheel, and you can turn the thing like this, and you can bring the rope up with a crank, and then you can send the rope back down again with a crank. And then somebody else made an invention, and they said, look, if you put some bacon grease on the wheel, it turns a lot easier. Wow, lubrication. And so what is the consequence of this whole series of inventions? It makes it possible to get the water up from the creek or from the well easier and easier and easier. Each invention makes it less work to get the water up. Now, you don't have to be all that smart. You can just be a tiny bit smart and a bit of a dreamer and close your eyes and think, in each generation we make an invention that makes it easier to get the water out of the creek. Maybe sooner or later somebody will come along and make an invention where you can get it out, you don't have to do any work at all. All right? What the heck? For free. Reminds me of an old friend of mine who got a car. It was an old wrecked car. Hardly go at all. And his father told him to put some air in the tires and it would go a bit better. He was amazed how much better the car had. It was a real wreck. It was a kind of a wreck about to be destroyed. But put a little air in the tires and the car ran a lot better. And then he said, and why don't you clean the points and it would go better, and put spark plugs in it, it would go better, and change the air filter and it would go better. And of course it was a young kid with his first car, rather inexperienced kid. And he got the idea, gee, if you keep on doing all these things and the car goes better and better, it gets better and better mileage, maybe I could do something to the car and it would run forever without any gasoline at all. Great, great improvement. So it's easy. It's easy to get the idea that you can make things that will run better and better and better. And finally, someday, maybe you could make a car or you could make a bucket lifting machine. And once you started it, you might have to start it, but once you started it, this machine would run on and on and on and on and on and on forever. Of course, again, you say, well, you're still getting something for nothing. Why in the heck would people believe that you can get something for nothing? I see that. I see your stories. Your stories are believable. But after a while, by the time you got people who were smart enough to understand Pythagoras' theorem, wouldn't those people, the fact that nobody has done it or got near to it makes it kind of questionable. Why wouldn't they see that? Let me talk about nobody's done it, nobody's got near to it. Are there no perpetual motion machines? What about the Earth spinning in space? Isn't the Earth spinning a perpetual motion machine? The answer is yes. It turns out that there are actually two kinds of perpetual motion machines, and we should stop and appreciate that right now. There's one kind of perpetual motion machine that's like a frictionless wheel. A frictionless wheel will spin forever providing you don't touch it. In other words, you can't make it do any work for you, because as soon as you put a pulley on it and attached it to your washing machine, or put a pulley on it and attached it to a pump, or put a pulley on it and attached it to an electric generator, all those things put a force on it and they would bring the wheel to a stop. But it's true, if you can have 100% lubrication, you can start a wheel and the wheel will spin forever. And there are examples of superfluids and wheels, or planets going around the sun in empty space, or even the electrons spinning around the atoms, and they go on forever. but the reason is that they're frictionless and you can't touch them. You can't take any power out of them. They will run only so long as you leave them alone. And those things are called perpetual motion machines of the first kind. But to be practical and useful, what you want is a perpetual motion machine of the second kind. Now, what's a perpetual motion machine of the second kind? That's a machine that will turn and turn and turn, and even when you put a belt and a pulley on it and you make it do work, and now it's not only turning, but it's dragging something with it, like pulling a train behind it, it will keep on going, unabated, without any fuel, doing work, pulling something. That's the kind, a perpetual motion machine of the second kind. And of course, I'm not going to keep on saying first kind and second kind, but you can realize that the kind that these practical people wanted in the olden days was a perpetual motion machine of the second kind, so it would crank out some work. Now, why did they believe it? Why did they persist in thinking that there was still a possibility of it? I'm going to show you why right now. What was in their mind that made them think it might be possible? I'm going to draw something long ago, and it's a very impressive thing that I'm going to show you. I can remember when my father first showed me this. I was a kid. I must have been younger than 3 years old, and I can still remember where my father took me. He took me to a playground in San Francisco called Holly Park Circle. It's a Holly Park Circle. And this is what he showed me in Holly Park Circle. There was a long board there, and it was balanced. It could go back and forth, go up and down. Of course, you know what it was. It was a seesaw. And the Greeks knew about seesaws too. They have been invented a long time ago. And my father sat at this end of it, like so. And I was a little guy at that time. I sat at this end. And the amazing thing was that even though my father must have weighed, I don't know, 150 pounds, and maybe I weighed 50 pounds, I balanced my father. What do you think of that? Is that picture drawn right? You notice the picture? You're right. The picture is not drawn right, is it? It's supposed to be put this thing will work, but it will work if I put the thing over there. I did that on purpose. I want to tell you something. Besides telling you about levers, I want to tell you something about physics. You know, if you come into a French class, in the beginning class or the second class, and it's your beginning French class, how much French do you know? You know zero French, unless you're a French kid who's getting credit for taking the French class, which is really cheating, but it happens all the time. But if it's an honest-to-God deal, you know zero French in your French class. But when you come into a physics class, you don't know zero physics. You see, you knew that right away. You saw I drew that wrong right away. You know one heck of a lot about physics. In fact, I suspect a lot of people looking at me are older than 20 years old. So you've been walking around the earth at least 20 years. Even if you'd only been walking around the earth for 10 years, you couldn't walk around the earth for 10 years without understanding quite a bit about how physics works. So you don't come in to physics class with an empty head. So one of your jobs, of course, you got a lot of ideas about how the world works. And one of the really important things is to see that the things you already know about physics correspond to the theory that I'm going to tell you about, or that you would read about in a physics book, or that somebody else would tell you about. Now, a lot of people think that what you learn in class is one world and you just memorize it for the teacher and spit it out or recite it on the problems, but that's not real physics. Real physics, to really understand it, it has to fit with the outside world. And if it doesn't fit with the outside world, then you have to, first of all, ask the teacher. Maybe the teacher won't be able to help you. Look in the book, ask various people, ask amateur scientists, ask people at universities, ask physics students, but you have to pursue it down, and sometimes it's quite a bit of work to see that the things in the outside world actually do correspond with the theoretical things. You know, physics is not like psychology. In psychology, first of all, one year they decide that alcoholism is a sickness. And then the next year they decide that alcoholism is not a sickness. Changes whatever they want. Or one thing is homosexuality is a sickness, or homosexuality is not a sickness. It just changes back and forth. In physics, you can't say black is white one day and white is white the next day. There really is a right way of understanding it. And so the things in class, there's not such a thing as classroom physics and outside the classroom physics. If it seems to you that way, then you're missing something. Okay, well, so much for this. Now, back to Holly Park Circle. Here's the seesaw drawn the right way, and this was known to the Greeks that you could balance this way. And what is amazing? Now, what's the amazing thing about this? The amazing thing about this is that on the inside of this side, what are you putting into here? You're putting in, on this side, 50 pounds of force. That's what you're putting in on my side. What's coming out on my father's side? What's coming out of here? What's coming out of here is 150 pounds of force. You surely are getting something for nothing if you can put in 50 pounds here and come out with 150 pounds. That's getting something for nothing, and everybody knows that it works, that a seesaw works. You can get something for nothing in physics, and here's an example of it. And the Greeks said to themselves, and the Babylonians and the Egyptians and the ancient Israelis must have said to themselves, look, if you can do this, then maybe there is a way that you can do a little bit of work here and out over here through this complicated machine, or out over here through another complicated machine. We can get more out than we put in. Okay, good enough. Now I want to talk a little bit about the problem of astrology, which was the original problem of astronomy. And remember, if we can somehow tell where the planets will be in the future, then we can tell where we will be in the future, because there's this idea that we are controlled by the sun and the moon and the stars and the planets. Now let me tell you a little bit about how the sky works so you can appreciate the problem in detail. If you look up at the sky, you'll see that there are certain stars in the sky tonight, and the stars that you see in the sky tonight have certain positions. And if you come back tomorrow night, the stars, and you look up again about the same time of night, the stars will have the same positions. And if you look up another night, the stars will have the same positions. And even without having any experience, and I bet that many of my listeners have never really done that, but you can know that it's true because these stars have names, like the Big Dipper or Orion, which means that a certain group of stars looks like the Big Dipper. Now, if the stars moved around, they might look like the Big Dipper tonight, but then in a few nights from tonight, they wouldn't look like the Dipper anymore. And the fact that they keep on looking the same way for ages and ages and ages, so you can talk about Scorpio and the great square in, what is it, the great square in Pegasus. The fact that these names go on means that the stars have the same positions. Year after year after year, they stay in the same positions. Now, that when I say they stay in the same positions, I mean there's a certain arrangement of stars in the sky. Of course, just like the sun moves across the sky, and the sun rises and the sun sets, all the stars, all the constellations move across the sky too. So, I mean, up comes Pegasus, and then up comes Orion, and they move across the sky. And just like typically it takes, if you see a star rising, well, if you see the sun rising, about 12 hours later, or roughly 12 hours later, the sun will set. Same is true of a star. If you see a star rising, About 12 hours later, that star will set. Not only will that star set, but the whole constellation that it's in will come up and come down. And that's the way it is for almost all the stars in the sky, except there are a few things in the sky that look like stars, but they're not. They're not because they have this peculiar characteristic. One day you'll look and you'll see the constellation of Orion, and suppose this is the constellation of Orion. Orion looks like this. See, he's a hunter. He has a belt, 3 stars in the belt, and this is supposed to be his sword. Then he's got some more stars out here for shoulders and arms and whatnot. But in addition to all this, over here there might be an extra star. And then after a while, you'll look, and this star won't be there anymore. It'll move over here. And then if you look, it won't be there anymore. It'll move over here. And then if you won't look, it won't be there anymore. It'll move over here. And then it won't be there anymore. It'll move over here. These stars wander around in the sky, and they were given the name planet. And I believe that planet is a Greek word that literally means wanderer. That's what they were. They were wandering stars. And there were a few of them. Let's see. There was Mercury, and there was Venus. The Earth's a planet, but those people didn't know it, so they wouldn't say the Earth was a planet. The Earth was not a planet in those days. Mars. Then there was Jupiter and Saturn, and maybe the sun and moon. They might have been planets too, maybe not. But these things wandered around. Now, they didn't wander around just like stagger through the sky like drunks. It turned out that they wandered around the sky. They all moved gradually to the east. In fact, if you watch them, if they keep on moving to the east, to the east, to the east, to the east, since the dome of the sky is round, how far can you go to the east on a dome? Well, if you have a dome, or I should not say a dome, I suppose I should say a sphere. If you keep on going to the east, to the east, to the east on a sphere, pretty soon you'll go around and come back to the west. They'll make one complete circuit through all the constellations in the sky, actually move through a certain part of the sky, and they get all the way around in a certain amount of time. And in fact, if you watched for a while, you could find that the one Mars would get around in about 2-3 years. It would make it all the way around. And the one Jupiter, it would make it all the way around in about, 12 or 13 years. And the one Saturn, it would make it all the way around the sky and came back in about, say, 30 years. Now, if you were controlled by these things, and there was a feeling in those days, and we'll come back to the reason, you could say, why did people think they were controlled by the planets? Why did people think that? Well, we're going to come back and talk about that a little bit. But if you felt that you were, say, controlled by Jupiter, if you were born and Jupiter was in a certain constellation, and then little by little by little it would move around, and maybe when it was halfway around from where it was when you were born, something important would happen in your life. And when it was all the way around, something would happen important in your life. And so you could tell exactly when those important things were going to happen in your life. And all you had to do was be able to know exactly when it was going to happen. Now you'd think, well, that's pretty easy. This is a real easy problem, because we know that Jupiter is going to make one complete trip around the sky in 12 years, and therefore we could figure it's going to go 1/12 of the way in 1 year. And we can see where it is and figure out what 1/12 of a complete circle is. As you'd say mathematically, what is 1/12 of 360 degrees? You could figure how much further to the east Jupiter would be in 1 year. And in fact, that works pretty well. You can do that roughly. You can make progress by thinking that way. You can make progress. But Jupiter got a few tricks up its sleeve. It turns out that Jupiter just doesn't move smoothly to the east. Now, as soon as you begin to think you understand what it's going to do, Jupiter will go to the east and move smoothly, and then it will come to an abrupt stop. And for a month or so, it'll just stand there in the sky. Just stand there. And then it will keep on going. And well, okay, now I know that every so often Jupiter stands still in the sky, so what I can do is I'll allow for that. You watch it. I remember what happened. Every December it stands still in the sky. So along comes next December. Well, next December it doesn't stand still in the sky. But about January, it not only stands still in the sky, but it begins to go the wrong direction. It actually goes backwards a little bit to the west. And then it stops and it goes to the east again. Holy cow, holy cow. I didn't expect that. It's like little intricacies in a dance that it's doing. You know grossly what the dance is, but then you got to learn how to wiggle your toes and how to wiggle your arms and this and that. So every so often Jupiter stops in the sky, and then every so often it actually goes backwards in the sky, and you think after a while maybe you got that figured out. And then you look at Jupiter again, it comes along, and instead of coming to it not only comes to a stop, it not only goes backwards, but this time it moves a little bit to the north, not much to the north, and then it goes back to the south again, and then it begins going on to the east. In other words, it not only goes backwards and then goes forward, but sometime it actually goes backwards and then up and then forward. It makes a loop like this in the sky. So you have a thing that's gradually moving to the east, and it is going to make a round trip, making one complete trip all around the sky in about 12 years. But on the way, it does all these weird little things that you try to figure out that keep on screwing up your predictions. And the moon is another one. If you try to tell where the moon's going to be, it got a full bag of tricks. You think the moon's going to go once around the sky in a month, but it got a whole bag of tricks. It does, but on the way it goes fast and slow and goes here and there. It's got one heck of a bunch of tricks. So you can see that this is the kind of a problem that you can work on, and you can make progress. You can discover some of its tricks, and then somebody else can come along after you, and they can study it some more, and they can discover some more of its tricks. And then the people after that person can come along, and each person can come along and discover some new tricks in this. And you can see how this is almost the exact formula that I gave for the kind of a problem that's not impossibly hard, but also not very easy, where many generations of people come and work on it. It's like a pearl. Pearl has many layers. It starts out, and then there are many, many different generations of people work on it. And that's how it comes to be a science and a thing that continues on. Talking about that, about how these things work, you can almost see how it grows by seeing the way that people used to think about it in the olden days. The old way of explaining this was to say that the Earth is in the center of the world, as we all know, and a lot of people still think the Earth is in the center of the world, and maybe it is for all I know. And there is a big wheel out here in space, and on this big wheel is Jupiter, and out here are the stars. And this big wheel that Jupiter's on turns around the Earth, and it goes around once in 12 years. But of course that won't quite account for its motion. Now you could say, well, this wheel stops and begins to turn backwards every so often, but the old-time people wouldn't like that, because they believed that if something began turning in heaven, that it had to turn smoothly and continuously forever. God doesn't like to start and stop things. But they found a way around it. They said, I know how to explain this. What they did is they say, on this wheel is another wheel, and on this wheel is Jupiter. Now look at what this is going to do. This wheel turns this way, but this wheel will turn, let's say, this way. So now Jupiter would move forward, but when this part of the wheel goes here, look which way Jupiter will be going here. It will be going backwards. See how that will be able to make Jupiter, here it will go forwards, this speed plus this speed. Here it will go backwards, this speed minus this speed. So speed will change. And then you discover that Jupiter does something else that's weirder still. And so the next scientist that comes along says, Jupiter is not on this wheel. There's another wheel here like this that turns in a certain way. And Jupiter is on this wheel here. And this is Jupiter right here. And there's Jupiter. And you can see how you build on this and build on it and build on it. And that's the formula by which astrology grew. And that's the formula by which many sciences grow. As you know, it's always our custom to end one of these talks with a question. And tonight we have a very serious question. This is not a school question. This is a question that bothered people, bothered scientists. Oh, I would say it bothered them from the time of the Greeks, and it probably wasn't clearly answered up until the time of Galileo. I don't even think Galileo could clearly answer this question, though he could come pretty close. Sometime around the age of Newton, the question was clearly answered. By the time of Newton, the answer was clearly known. And here is the question. You remember, the reason people want a perpetual motion machine is because they want to do work. That's what they want to do with it. They don't just want to sit and watch it run as a toy. They want it to do work. But now comes the question of what is work? Now, in particular, that's part of the question, what is work? But the question is sharper than that. Here is the lever again. And you remember with the lever, if you put in a certain amount of force here, say you put in 5 pounds here on this end will push up with a certain force which will be much greater than 5 pounds. In this case, it's maybe 5, 10, maybe 15 pounds. You get 15 pounds of force will come out of here. Now, the specific question I want to ask you is, what is work? More than that, what is the difference between force and work? Supposing I say, well, I know what work is. Work is force. Force is work. Or force is energy. Energy is work. Is force work? Yes or no? And if the answer is no, then what is the difference between force and work? And that's what I want you to think about. We'll begin, in fact, that will be the subject of the whole next talk. We'll go into that, what work is, and we'll see if force is work or if it's not.